My name is Maria Khalusova. My Twitter handle is the same as my name. I work for JetBrains. I also organize a PyData Montreal, so if you're ever in the area, please stop by. We have a very nice user group, and we have a lot of interesting talks. And this particular talk has been born out of my frustration in the early days of learning about machine learning, and then after training a few models and being happy with my accuracy and whatnot, realizing that on Kaggle, for example, you see competition and there's F1 score and ROC and log loss and a lot of other metrics, and you start Googling and it's like, what is that all about? And why are there so many? And what do they mean? And how do I choose? And if I try to do my own thing, like which one is better for me? So for those of you who are new, this is going to be a talk that's supposed to save you some of that time and that Googling. And if you are an expert, maybe this will be a refresher on some of the metrics. So evaluation metric is basically a way to quantify the performance of a trained machine learning model. And it is not the same as a loss function. A loss function is something that is used during the training, something you optimize for. And evaluation metrics is something that lets you, that gives you a number that tells you how good your model is or how bad it is. It lets you compare different models and choose which one is better. And we're going to talk about supervised learning metrics, specifically for classification and regression. I'm going to try to cover this bunch of metrics, and if things will get boring, we'll throw some formulas in there, and it'll be fun. We're going to start with classification metrics, and to make things a little easier, I'm going to focus first on binary classification. And first metric, of course, that everybody encounters when solving a classification problem is accuracy, which is very intuitive to understand. It's a number of correct predictions out of a total number of predictions, and it ranges from 0 to 1 or to 100%. And it is very simple and very easy to understand. You can get it in scikit-learn. For example, here I built a simple logistic regression on some data, and I got nearly 96% accuracy. Accuracy here is returned with the score method that every model has, and 96%, woohoo, that's great. So my job here is done, right? Or not? We don't know. The thing is, if I build a dummy classifier on the same data, the dummy classifier that returns most frequent values, so it doesn't really learn anything from the data, gives me 94% accuracy. And why is that? The thing is, you don't know because I didn't show you my data. And for this example, I just made a classification problem where if you see, there's 95% of samples are negative and only 5% are positive. So this is a class imbalance data set. That's why simply predicting most frequent value is going to give me 95%. In this case, 94% is because of how the data got split. So, 96% accuracy. Is it good or not? I don't know. Depending on your data, the number alone doesn't tell you anything. And even if it was a balanced data set and we wanted to improve and learn what kind of errors the model is making, accuracy alone doesn't really tell you much. So we need some other tools if we want to improve. And lucky for us, there's a lot of tools, there's a lot of metrics. And first of all, there's confusion matrix, which is not an evaluation metric, but more of a diagnostic tool to see, to get insight into the type of errors your model is making, and it's also very useful to understand other metrics that can be derived from it. So here, I'm going to build some random classifier on the, this is from Titanium data set, which this actually is not a very bad result, but I still want to improve, so I'm going to take confusion matrix, import confusion matrix. Sorry about that. I'm going to import confusion matrix from scikit-learn metrics, and I'm going to get this beautiful array. An important thing here is if you're building confusion matrix to pass the true values first and then the predicted values. And then if you've never seen a confusion matrix before, this may be confusing because it's just an array. And what does it mean? That's why typically it's drawn like a table, like this one. So in the rows, we have the actual values, and in the columns, we have the predicted values. This is a convention that is used in scikit-learn, TensorFlow, and other tools, but there are tools out there that have it the other way around. So if you're encountering articles, or even Wikipedia page has it the other way around, so be careful if you're reading some confusion matrices in the articles. It may not be the case like here. They may have true values in the columns. So this is something to pay attention to. Now from this, we can see that we have what is called true negatives, true positives. True negatives are the ones where the predicted value was 0 and the true value was 0. And we have false positives, false negatives, true positives. If we just sum up true negatives and true positives and divide it by the sum of everything in all cells, we get the accuracy. But what would be the point of showing you confusion matrix if I just wanted to explain accuracy? Of course, there are other metrics that we can get from the confusion matrix. And for example, there's precision. Precision is calculated this way. You take the true positive values and divide it by the sum of true positive and false positive values. What does it mean? And when do you care? Let's take an example of a spam detector. That's a classic example. A false positive in this case would be marking let's say, invitation to speak at a conference and put it in a spam box. And you really, as a user, don't want that. You don't want to fish through enlargement offers to find your invitation to a conference. And this is very annoying for users too. You really, really want to minimize false positives. In this case, that is when you care more about precision. Because if you minimize false positives in precision, the whole metric improves. It goes closer and closer to 1. Now, in some cases, you care more about false negatives. For example, a classical case would be medical diagnosis for some serious disease. It would be better to send a healthy person for more tests compared to sending home somebody who really does have that disease, which would be a false negative. In this case, you would care about metric called recall. And as you can see from the formula, if you minimize false negatives, then the whole metric improves. To me, a helpful mnemonic to remember which one is which was that precision is all about positives. So P, true positives, false positives, precision. Otherwise, the names to a person coming from a different field, they don't really make much sense. There's also a metric called F1 score that allows you to combine the two, and is basically just the harmonic mean of precision and recall. So to summarize the difference between the two, if you care more about the positives, false positives, then you should check your precision. If you care about minimizing false negatives, then you should care about recall. And this really depends on the business problem you're trying to solve. What is the task you're working on? Unlike confusion matrix, precision, recall, F1 score are all just numbers that you can compare. You can get them with scikit-learn.matrix, for example. And you can use them already to compare different models. For example, if you are doing a grid search and you go through some parameters and you can specify a scoring parameter. For example, in this case, is recall, and you're going to get an estimator that gives you the best recall out of all of those models that you went through. There's also one more way to summarize confusion matrix, which is called Matthews correlation coefficient. And what is important to notice about this formula is that it takes into account all 4 cells of the confusion matrix. And this is important. It has its consequences. And I'm going to show you a couple of examples. Let's say we have some data, 100 samples, 95 positive, 5 negative. And we're going to just use a dummy classifier. So this is what a confusion matrix is going to look like for it. The accuracy on this one will be 95% naturally, and F1 score is even a little bit better, but MCC is going to be, well, scikit-learn is going to return you 0 with a huge red warning saying that is technically undefined because you're dividing by 0 here. And among all 3 metrics, accuracy, F1 score, and MCC, only one of them gave you a red flag that something's fishy is going on about this model. And it is, because it's a dummy classifier that doesn't really do anything. Here's another example. We're going to take slightly more interesting case. So now we have a model that actually predicts something, so that we have some true negatives, some true positives, some false positives, and false negatives. F1 score is going to be 0.952, MCC 0.135. But what are we going to do now is we're going to flip what we call a positive class and what we call a negative class. So now everything stays the same, the model is the same, but what we call a positive and what we call a negative is different. So it's kind of, the matrix is going to be a little mirrored. In this case, F1 score now is different. It's 0.182. MCC is the same. And this is because F1 score is sensitive to which class is positive and which class is negative. And MCC is not. It takes into account all 4 cells, while F1 score doesn't take into account the true negatives. So when using, when working on the binary problem and looking for a metric to summarize the whole confusion matrix, I find that MCC works better, but unfortunately it does not extend nicely to multi-class problems, so we have to work with some other things. Now, up until this point, all the metrics that are shown, they only took into account whether the prediction was correct or not. But a lot of classifiers, they output a probability of an example belonging to one class or the other. And there are metrics that take that into account. For example, ROC curve. ROC stands for Receiver Operating Characteristic. Raise your hand if this explanation of acronym helps you understand the metric. That's what I thought. So it's a plot. ROC curve, it's a plot where on the y-axis you have true positive rate, which is the same thing actually as a recall. Yay, machine learning naming several things, the same thing with different names. And on the x-axis we have false positive rate. The first time I saw this curve, my thought was like, why is it not a dot? Why is it a curve? And this is where the probabilities come to play. When a model outputs a probability of a class belonging to one, of a sample belonging to one class or the other, there's always a probability threshold, by default 50%, in which we decide if it belongs to positive class or the negative class. But we can move that threshold. And then as we move it and say, we decide that we are going to predict positive class only if the probability is higher than 80%. But if we do that, the values of true negatives, positives, and so on and so forth, they change. Why? If we had an example that was 60% probability that it's a positive class, and before we defined it as a positive, we labeled it as a positive class, and was actually a positive class, it was a true positive. We moved the threshold to 80%, and now we say it's a negative class. Now it becomes a false negative. So what we do here is essentially we move this threshold, and for each threshold, we calculate true positive rate and false positive rate, plot the dot, connect it, we get the line. The next question would be, is it a good one or not? Which one's better? And to me, it helps to think of what it would look like in the perfect case scenario when there is a threshold at which we can classify samples without making a mistake. In this case, the dot will be here in this corner because we will not have any false negatives. So we're going to have 1 on y, and we're not going to have any false positives, so it's going to be 0. And as we change the threshold, we're going to be plotting lines, dots either here or here. So in ideal, unrealistic unicorn case scenario, the curve is going to be hugging that corner really, really tightly. So that's what we want to have. So this is, again, a very nice visual tool to compare models. We can plot the curves for different models and see which one is better. But as a metric, it's better to have a number to compare different models. And that's why we have AUC, which is simply the percentage of this box that is under the curve. And in ideal case scenario, it's going to be 1. And in this case, it's going to be, I don't know, 70%, something like this. This already we can calculate and we can compare. There is also another curve, precision recall, which has the same exact mechanics to it. So we're going to be moving threshold, calculate the metrics, and plot them. Instead, in this case, we're going to be plotting precision and recall. What is the difference? When will I choose one over the other? It goes back to class imbalance data. If we take the same data set, and then we plot, okay, I'm going to, there's going to be 95% of it negative, 5% is going to be positive. We're going to get the probabilities and plot the curves. So ROC is going to be looking pretty good, whereas precision recall curve is showing a more complete picture of what's going on. So be careful when using ROC curve on class imbalance data. Another metric that takes into account the probabilities is log loss. This is also a common loss function. And what it does, it takes into account the uncertainty of model predictions and gives a larger penalty for confident and false prediction. This is the formula for the binary case, and I'm not going to go into explaining the formula. I'm going to give you the intuition of how it works. So if you have a true label of 1, a predicted probability of class belonging to 1 is 0.9, we're going to have a relatively low log loss. But the more wrong and confident we get, the log loss skyrockets. So this metric, compared to accuracy, it gives us a chance to take into account not only how correct our predictions are, but also how confident they are. Now, how do we extend these metrics to a multi-class classification? The confusion matrix, you can also plot it for a multi-class classification. And typically, you would plot it as a heat map. I'm not going to give a code example, but it's pretty easy to do. In this case, this is a confusion matrix for a model built on the digits toy data set from scikit-learn. So the labels 0 to 9 are actually the handwritten digits 0, 1, and to 9. And in the same case as with binary classification, you have true labels in the rows and predicted labels in the columns, and you can analyze like what sorts of mistakes your model is making. For example, a number 8 has been confused for number 1 3 times, and number 2 was confused for 3, and so on and so forth. But in this case, we don't really have true negatives and true positives in the pure sense, like we did with the binary classification. But we still can use metrics such as precision recall and F1 score. And there are different ways of calculating them. Here, for this sample problem, I calculated them 3 times with different averaging. There's macro averaging, micro and weighted averaging, and the numbers are quite different. So to calculate the metric like precision on a multi-class problem, what you do is you think of your problem as a set of a binary one versus all problems. Then you calculate the metric and you average them. Let's see how we can do this. For this problem, we're going to build a confusion matrix. It's pretty straightforward. Then we're going to calculate for each class the true positive and false positive. I'm not going to take false negatives because I'm going to calculate only precision for this example. So let's say we have a bird. The true positive is going to be every time we said it was a bird and it was in fact a bird. So there's going to be this one cell. And true positives are basically the same as in binary case, are all on diagonal. So for a bird, it's going to be 1. False positives is going to be every time we said it was a bird, so we predicted a bird, but it wasn't. So all the values in the column here except for the true positive values. So in this case, it's 0. And false negatives would be every time we said something else, but it was a bird. So it's going to be in the row. We do this for every class, and we're also going to write down some totals. How many total true positives we had, how many false positives we had. Now we can calculate precision per class. So 1 divided by 1 plus 0, 1, 4 divided by 4 plus 1, 0.8, and so on. And we're going to write down the number of samples in each class. So now, micro-precision, we're going to take the totals to calculate it. This way, every sample contributes equally to the final average. Macro precision, we're going to take the average of precisions calculated per class. And weighted precision, we're going to take again precisions calculated per class, but we're going to take into account the size of the number of samples that we had for each class. Now, what does it give us? So, in the micro-average case, all samples equally contribute to the average. In the macro-average case, all classes equally contribute to the average. And in weighted average, each class's contribution to the average is weighted by its size. When do you choose what? Well, again, it depends. Depends on whether you have class imbalance data. If your underrepresented class is important or not. If you have an underrepresented class that is important to get right, then you can use macro-average to amplify its contribution to the average. If the assumption that it's equally important is not true, you can use micro-averaged or weighted average. In the multi-label settings, scikit-learn documentation recommends using micro-average, but I'm not an expert on multi-label. I haven't done much there, and so I'm just going to trust them on that. And multi-class log loss is basically the a broader version of the log loss for a binary case. The formula looks a little bit different. If you don't like formulas, I spelled it out here as some 4 cycles. So basically what's happening here, y is, n is the number of observations. M is the number of possible classes. Y is a binary indicator if, for an example I, Y is the correct, J is the correct label. And then there is a logarithm of probability of this label being correct, of this label for this sample. And then we just go through them and sum them up. In scikit-learn, of course, it's implemented differently. They have vectorized operations, but to me, it helps to understand this formula by just simply writing it out like this. Now, the next thing is regression metrics. And even though with regression metrics there is a little bit more formulas, I find that conceptually they're a little bit easier to understand because you don't have probabilities, you just have a continuous target value, you have continuous predicted value, you take the difference, which is called error or residual. And then the question is, how do you define performance of the whole model based on individual residuals? And there's, of course, a number of ways to go about it. One, which is the default metric that you can get for scikit-learn regressors through score method, is called R-squared, or coefficient of determination. And it's conceptually similar to accuracy, so it is a value that does not depend on the units of the target value, and it gives you an idea of how close the model predictions approximate the true values, where 1 is the perfect fit and 0 is R-squared of a dummy regressor predicting average. And basically, if you look at this formula, at the bottom here, the denominator, you have actual values minus the mean, and it's the distances between the actual values and the mean are squared and summed up. And then at the numerator, you have the difference between the actual values and predictions. They're squared and summed up. And if your model is a dummy regressor, this will be equal. This will be 1, so you're going to get 1 minus 1, 0. If your model is really, really bad, and for example, is always predicting infinity, then you can even get to a negative R-squared. And if you're doing better than the dummy regressor, then you're going to be getting closer to 1. So this is the intuition for this one. But one of the problems with R-squared is that it doesn't really give you any information about the prediction error. And in regression tasks, very often you care about how far off are you, not just how close you are, relatively to the true values, but what is the actual error. And there are many metrics that can help you with that. The first one would be the mean absolute error. What we do here is take the residuals, take the absolute value of them, and take the average. It's pretty straightforward. You can get it from scikit-learn metrics as a mean absolute error, or you can write it yourself. I don't know why would you, but then if we don't take the absolute value but square the residuals, then we get what is called mean squared error. And the problem with this one is that now we're talking about squared units of the target value. And this is why typically you would go for root mean square. We just take the root out of this, and you're back to the units of the target value. What's the difference between them? They are really the mean absolute error and RMSE have a lot in common. They both range from 0 to infinity. They have the same units as target values. They don't care about the direction of the errors. And the lower the metric is, the better. But there's a lot of debate about which one would be a better evaluation metric. So some differences between them is that RMSE gives a relatively high weight to large errors because the residuals are they're getting squared before they're added to the average. And this makes mean absolute error more robust to outliers. Another difference would be that RMSE is differentiable, but this would matter only for a loss function. In the case of choosing evaluation metric, it doesn't really matter that much. There is a lot of debate which one is better, and you can find a lot of articles on this. And I think that most of them are coming from a paper by Wilmot and Matsura from 2005, where they claimed that RMSE is inappropriate metric for evaluating the average error. But as it happens, 4 years later, there was another paper that said, well, this is not the case, and RMSE is actually a fine metric, and if the distribution of the errors is expected to be Gaussian, which is most of the time the case. And if you have a really, really tiny, small test set, neither of them is actually going to be robust. But for most of the practical purposes, I find that RMSE is doing just fine, and you only want to use absolute error if you really want to downplay the outliers. One version of RMSE called root mean squared logarithmic error is sometimes very handy when you have exponentially growing targets. For example, if you have prices ranging from, I don't know, $5 to 50,000 and so on and so forth, this gives you a way to sort of get a relative error. And for example, by taking the logarithm of the target value and the predicted value, you can have $5 error in $50 purchase matter more than $5 error in 50,000 purchase. So this gives you a bit of a scale. But you can also use a regular RMSE and scale the target values, for example. That's depending on what you prefer to do. So we've just made a quick tour of different metrics, and what I don't expect you to fully understand all of them right away, and I have some links later in the slides. But what's important to know and to take away from this talk is there's no one metric that's going to cover all the cases, and depending on what kind of data you're working with, you may prefer one metric over the other. And the important thing is to know what you're actually trying to do. And this will help you choose the right metric. Thank you. There's more links if you want to read some more.